Greetings of the day to all of you. Having completed our discussions on selective harmonic elimination technique and also offline optimized PWM techniques, which is also called stored waveform PWM. Today we are going to discuss another type of low switching frequency PWM, that's called phase modulation. Phase modulation. Let me draw the power circuit diagram of a single phase voltage source inverter. We are already familiar with this circuit topology. This is the power circuit diagram of a single phase PWM voltage source inverter. This is VDC by 2. This is also VDC by 2. This is midpoint of the DC bus capacitors, and this is the total DC bus voltage, VDC. Let me call this switch as TA plus. This switch I will call as TA minus. This switch I will call as TB plus, and this switch I will call as TB minus. This voltage source inverter, as you know, it is composed of 4 two-quadrant switches which have bidirectional current carrying capability and unipolar voltage blocking capability. Okay, we already know about the square wave operation of this inverter. In square wave operation, the pole voltages are like this. This is, for example, pole voltage VAO. Voltage of this pole with respect to midpoint of DC bus capacitors. VAO is pole voltage. So it is like this. It is plus VDC by 2 and minus VDC by 2. From 0 to pi, it is plus VDC by 2, and from pi to say 2 pi, it is minus VDC by 2. And that means from 0 to pi, these two switches are turned, this switch is turned on. When this switch is turned on, the pole A gets connected to positive terminal of this DC bus capacitor, and voltage of pole A with respect to O is this. So this is the voltage across pole, between pole A and 0. So pole voltage VAO is plus VDC by 2. And when bottom switch TB minus is turned on, then this A gets connected to this negative terminal, okay, or negative DC bus. So VAO in that case is minus VDC by 2. That's what we get. So that is about pole voltage VAO. So VAO is plus VDC by 2 when TA plus is on, and it is minus VDC by 2 when TB minus is on. Let us consider this arm. In this arm, upper switch or lower switch can be on. Okay. So in the second arm, I can have pole voltage VPO like this. So I will write VBO pole voltage. So what I will do, I will put this TA minus switch on. When TA minus is turned on from 0 to pi, this B gets connected to negative DC bus, and VBO is minus VDC by 2. So this is pi. So VBO is, this is pi. VBO is minus VDC by 2. And then from pi to 2 pi, this is 2 pi. I am turning upper switch on, TB plus on. So B gets connected to positive DC bus, and VBO, VBO is plus VDC by 2. So it is plus VDC by 2. So that means from 0 to pi, when you consider this leg or this arm, TA plus is on from 0 to pi, and in this arm TA minus is on from 0 to pi. So what will that do? That will connect terminal A to positive DC bus, and that will connect terminal B to negative DC bus, and total voltage across the load between A and B is full DC bus voltage. In terms of pole voltage, we know that load voltage VAB, which is equal to V naught, that is given by VAO pole voltage minus VBO pole voltage. And since you have already drawn these pole voltages, so you can add up, you can subtract the two pole voltages, and you will get the voltage across load VAB, which is equal to V naught. So from 0 to pi, for example, you can see this is pole voltage VAO is plus VDC by 2, and pole voltage VBO is minus VDC by 2. So this minus this, so this becomes plus VDC by 2 plus VDC by 2 is plus VDC. So from 0 to pi, the load voltage VAB, which is also equal to V naught, is VDC. That is from 0 to pi. What about pi to 2 pi? From pi to 2 pi, again, VAB is VAO minus VBO. VAO is minus VDC by 2, and then minus VDC by 2. Minus VDC by 2 minus VDC by 2 gives minus VDC from pi to 2 pi. So my load voltage is minus VDC. Okay, so this is my load voltage. Okay, in terms of pole voltages, this load voltage VAB is pole voltage VAO minus VBO, and this is what we get. And you can see that from 0 to pi, TA plus and TA minus are turned on, so load directly gets connected across the DC bus, with A connected to positive bus, B connected to negative bus, and VAB, which is V naught, is equal to plus VDC. And from pi to 2 pi, these two switches, complementary pair of switches is on. TB plus and TB minus are on. So that connects B to positive bus and A to negative bus, and VAB becomes minus VDC. Okay. So therefore, we can see the two pole voltages, VAO and VBO, are 180 degrees out of phase with respect to each other. See, this is VAO, it's positive from 0 to pi, whereas VBO is negative from 0 to pi. On the other hand, VAO is negative from pi to 2 pi, whereas VBO is positive from pi to 2 pi. So that means the two pole voltages, VAO and VBO, are 180 degrees out of phase with respect to each other, which gives our load voltage for positive half cycle equal to VDC, and for negative half cycle equal to minus VDC. And the fundamental component of the load voltage will be this. Let us call this VO1, fundamental component of voltage. Okay. Now, if the two voltages are in phase with each other, I mean, if the situation is like this is my pole voltage VAO. So as usual, it is plus VDC by 2 from 0 to pi, and it is minus VDC by 2 from pi to 2 pi, plus VDC by 2 and minus VDC by 2. If I make second pole voltage VBO same, I mean in phase with VAO, this is 0 to pi and this is pi to 2 pi, I mean it is in phase, it is also plus VDC by 2 from 0 to pi, and it is minus VDC by 2 from pi to 2 pi. How is that possible? That is possible only, say if you take pole voltage VAO from 0 to pi, VAO is plus VDC by 2. That's possible only when TA plus is on. So TA plus is on makes A getting connected to positive DC bus and VAO equal to plus VDC by 2. During the same period, VBO is also made plus VDC by 2. That means instead of conducting this switch, what we are doing, we are triggering or conducting this switch, upper switch, TB plus. So when TB plus is turned on, B gets connected to positive DC bus and VBO is also plus VDC by 2. Similarly, for negative half cycle of, for negative half cycle from pi to 2 pi, my VAO is minus VDC by 2. That's possible only when bottom switch TB minus is turned on. When TB minus is turned on, A gets connected to negative terminal or negative DC bus and VAO is minus VDC by and simultaneously in this leg, the bottom switch is turned on, that is TA minus is turned on, so B also gets connected to negative DC bus, and VBO is also minus VDC by 2. So that means in the positive half cycle, this and this switch TA plus and TB plus are turned on, and load gets short circuited by these two switches, and current may flow either in this direction or in this direction. So when load is shorted by these two switches, load voltage becomes 0. Similarly, in the negative half cycle, these two switches TB minus and TA minus are turned on, and load gets shorted by these two switches, and load current may flow in this direction or in this direction. So VAB or V naught is equal to 0. So therefore, if you see VB or V naught load voltage, which is VAB, it is 0 all throughout. It is 0 from 0 to pi and 0 from pi to 2 pi, because our V naught is equal to VAO minus VBO. From pi to 2 pi, VAO, that is VDC by 2 minus VDC by 2 is 0. From pi to 2 pi, minus VDC by 2 plus VDC by 2 is 0. So pole voltage becomes equal to 0. So in this case, the two pole voltages are in phase. When the two pole voltages are in phase, that makes load voltage equal to 0. And in that case, the situation is like this. From 0 to pi, upper two switches are on, and load gets shorted, and load voltage is 0. From pi to 2 pi, bottom two switches are on, and load again gets shorted through these two switches, and load voltage is again 0. So therefore, we have taken two extreme cases. In first case, we have taken the pole voltages VAO and VBO 180 degrees out of phase with each other, and that gave us square wave voltage across the load. That's maximum voltage that is applied across the load, that is plus VDC and minus VDC. From 0 to pi, load voltage is plus VDC, and from pi to 2 pi it is minus VDC. In the second case, what we did, we made load voltages in phase with each other, that is phi equal to 0. In that case, we found that the two pole voltages subtract from each other, and they make load voltage equal to 0. So this gives us an idea that if the phase angle between the two pole voltages can be varied, can be made variable, we can exercise a control over inverter output voltage, and fundamental component of inverter output voltage can be controlled, which is one of the objectives of pulse width modulation. So what we can do, just try to understand, this is my pole voltage VAO, and for example, this is plus VDC by 2 and minus VDC by 2. From 0 to pi, it is plus VDC by 2. From pi to 2 pi, it is minus VDC by 2, because from 0 to pi, TA plus is on, so VAO is plus VDC by 2. From pi to 2 pi, TB minus is on, so VAO is minus VDC by 2, right? What I will do, as far as pole voltage VBO is concerned, I will not make that 180 degrees out of phase with respect to VAO. I will make that like this. So for example, this may be my pole voltage VBO. So it is minus VDC by 2. So let me call this phase angle as phi. So phi is the phase angle by which pole voltage VBO lags behind pole voltage VAO. So this phase angle is variable. So this is minus VDC by 2 plus VDC. So what I am doing from 0 to phi, in this leg or in this arm, I am turning bottom switch on. When I am turning bottom switch on, my B gets connected to negative DC bus, and VBO is minus VDC by 2. But at phi, I am switching from minus VDC by 2 to plus VDC by 2 as far as pole voltage VBO is concerned. That is possible when this is turned off and TB plus is turned on. So when TB plus is turned on, B gets connected to positive bus, and VBO becomes plus VDC by 2 for this period. And then it remains plus VDC by 2 from pi to phi plus pi plus phi, and then it becomes again minus VDC by 2 and so on. And therefore, if you draw the load voltage waveform, VAB, load voltage VAB, which is equal to V naught, that's load voltage, you can see from 0 to phi. Let me draw these projections first. Now we can very clearly see from 0 to 5, your load voltage VAB, I have already written, that's VAO minus VBO. This is VAO minus VBO. So VDC by 2 plus VDC by 2, that's plus VDC. So from 0 to 5, my load voltage is VDC plus VDC. And from pi to pi, my pole voltage VAO is plus VDC by 2 and VBO is also plus VDC by 2. So VDC by 2 minus VDC by 2 becomes 0. So I am making load voltage 0 from pi to pi. Then from pi to pi plus phi, that is this point to this point, my load voltage is VAO minus VBO, that is minus VDC by 2, minus VDC by 2, that is minus VDC. Minus VDC. And then from pi plus phi to 2 pi, this is minus VDC by 2, this is also minus VDC by 2. So VAO minus VBO is minus VDC by 2 plus VDC by 2. So it is again 0 from pi plus phi to 2 pi. And then it again goes to plus VDC. So therefore you can see for certain periods from phi to pi and from pi plus phi to 2 pi, I am making load voltage 0. So therefore the RMS value of voltage across the load is 0. So therefore fundamental component of voltage across load decreases. I can decrease it further like this. This is pi, this is 2 pi, plus VDC by 2, minus VDC by 2. Pole voltage VAO, and this is my pole voltage VDO. My pole voltage, I can have my pole voltage like this. I mean, this may be my phi. This is phi, phase angle, by which VBO lags behind VAO, phi. It is plus VDC by 2, minus VDC by 2, and here also it is minus VDC by 2. Now you can see our load voltage will be something like this. VO will be equal to VAO minus VBO. So from 0 to 5, you can see VAO is plus VDC by 2, VBO is minus VDC by 2. So load voltage VO is equal to VAO minus VBO plus VDC by 2 plus VDC by 2, that is plus VDC. So it is plus VDC from 0 to 5. Then from phi to pi, this is my pi. My load voltage becomes 0 because you can see VAO minus VBO, that's VDC by 2 minus VDC by 2, it becomes 0. And from pi to pi plus phi, that is this period to this period, you can see my load voltage is VAO minus VBO, that's minus VDC by 2 minus VDC by 2, it is minus VDC. Minus VDC. And from this to this, up to 2 pi, my load voltage is minus VDC by 2 plus VDC by 2, it is 0. So now we can see I am applying even a smaller voltage across the load. Small segment here, small segment here. From 0 to 5, VDC gets applied across the load. From pi to pi plus phi, pi plus phi. Again a negative VDC gets, minus VDC, small negative voltage gets applied across the load. So therefore fundamental component of voltage further gets reduced. So therefore by controlling phase angle between the two pole voltages VAO and VBO, a controllable fundamental voltage can be produced across the load. So we can impress a continuously controllable voltage. I mean, the voltage can be controlled from 0 to, voltage can be controlled from 0 to fundamental component, peak value of fundamental component of voltage can be controlled from 0 to 4 by pi VDC. Because when maximum voltage is applied across the load, at that time your inverter is operating in square wave mode. And in that case, load voltage is plus VDC minus VDC. Plus VDC from 0 to pi, and from pi to 2 pi minus VDC. And fundamental component of voltage will have maximum value, and that is 4 by pi VDC. We have already made these calculations using Fourier series in module number 1. Okay, so that is of course in module number 2. So maximum inverter output voltage is 4 by pi VDC, and that is when phase angle between the two pole voltages 180 degrees, and square wave operation is resulted. This is square wave operation. And then if you reduce the phase angle between the two pole voltages, you can get a variable output voltage. And when phase angle is 0 between the two voltages, pole voltages, inverter output voltage will be equal to 0. For phi equal to 180 degrees, peak value of fundamental component of voltage is maximum, that is 4 by pi VDC. And for phi equal to 0 degree, fundamental component of voltage will be 0. So therefore, by varying phi from 0 to 180 degrees, 0, phi 1, 180 degrees, output voltage, peak value of fundamental component of output voltage varies from 0 to 4 by pi VDC. When phi is 0, the two voltages are in phase, output voltage is 0. As you increase phi, okay, the fundamental component of inverter output voltage increases, and when phi is 180 degrees, that means when the two pole voltages are 180 degrees out of phase with respect to each other, your fundamental component of voltage, inverter output voltage is square wave mode of operation, and fundamental component of inverter output voltage will have maximum value, that is 4 by pi VDC. Okay, so this can be represented in terms of phasor diagram also. If you draw the phasor diagram, let us consider fundamental component of pole voltage VAO. Okay, this is the phasor for fundamental component of pole voltage VAO. And let us suppose VBO is also equal to VAO. So VAO is equal to VBO, VAO1 is equal to VBO1. That means phi is equal to 0 degree. The two voltages are in phase with each other. So therefore, in this case, what will be VAB? Load voltage. It will be VAO1, the fundamental component of load voltage, VAB1 will be equal to VAO1 minus VBO1. Since the two voltages are in phase with each other, it is 0. So it will produce 0 output voltage. Okay? And the other extreme is when phi is 180 degrees. So this is VAO1, okay, and this is VBO1. Now in this case, phi is equal to 180 degrees. This is phi equal to 180 degrees. Pole voltage VBO is 180 degrees out of phase with VAO, and therefore what is load voltage VAB? It is, fundamental component of load voltage VAB1 is VAO1 minus VBO1. And it will have maximum value. This is VAB1, maximum value. It is the sum of the two voltages. And this will of course give square wave operation. And for a phase angle between 0 degree and 180 degrees, you will have a controllable or variable inverter output voltage. For example, this may be the fundamental component of pole voltage VAO1, and this may be the fundamental component of pole voltage VBO1. And VBO1 may be lagging behind VAO1 by phi, which is between 0 and 180 degrees. So what is therefore load voltage? Load voltage is VAO1, fundamental component of load voltage is VAO1 minus VBO1. So we can go for phasor, so So this is VAB1. This is VAB1, the load voltage, fundamental component of load voltage, which is VAO1 minus VBO1. I am adding the two phasors. This is minus VBO1. This is plus VBO1. This is minus V. So the total voltage is VAO1 minus VBO1. It's the fundamental component of load voltage. So it can be made controllable. It can be zero. It can be increased, and it can be made maximum. So therefore, by controlling the phase angle between the two pole voltages, VAO1, VAO and VBO, we can produce a controllable inverter output voltage. So fundamental component of inverter output voltage, it can be controlled. And the advantage of this method is that we are controlling the inverter output voltage from 0 to maximum. We are able to control the inverter output voltage from 0 to maximum at a very low switching frequency, because you see there is no switching at all. There are normal switchings. Okay, there are switchings from minus VDC by 2 to plus VDC by 2. Say for pole voltage VAO1, and for pole voltage VBO1, there is the switching from minus VDC by 2 to plus VDC by 2 after a phase angle of phi. So natural switchings. So therefore, the inverter output voltage can be controlled over a very wide range from 0 to maximum value. That means from 0 to 4 by pi VDC at very low switching frequency. So therefore, this application is also, it may be suitable for high power drives where switching frequency has to be kept very low. But the serious problem with this method is that although it is possible for us to control the fundamental component of inverter output voltage from 0 to maximum, it is not possible to have a control over the harmonics. Whether your voltage is, maximum 4 by pi VDC, or it is between 0 and 4 by pi VDC by controlling phase angle. Inverter output voltage is controllable, but there are strong harmonics present in the load voltage. For example, for the single phase inverter, you will have all triplen and non-triplen harmonics present in the load voltage. You will have third harmonic component of voltage, you will have fifth harmonic component of voltage, seventh harmonic, ninth, 11th, 13th, and so on. And if it is a three-phase voltage source inverter, then you will have all non-triplen harmonics present in the load voltage. That is n is equal to 5, 7, 11, 13, 17, 19, 23, and so on. So although inverter output voltage is controllable, but it will be very rich in harmonics, we will not be able to suppress or to eliminate the harmonics. That is the serious problem with phase modulation. That is why phase modulation is only of theoretical interest. We just study it for the sake of understanding that the inverter output voltage can be controlled by phase modulation. But since the inverter output voltage will be very rich in harmonics, it will not be possible for us to suppress those harmonics. Therefore, this method is generally not recommended. Okay. For a low switching frequency PWM, we generally go for selective harmonic elimination technique, or what we call as offline optimized PWM technique, where we can control the fundamental component of inverter output voltage, and simultaneously we can suppress certain selective harmonics for minimization of weighted THD, or for minimization of pulsating torque, or for some other purpose. Okay, so that is about phase modulation, and with this we conclude our lecture series on low switching frequency PWM. To summarize, we have learned how low switching frequency PWM can be used for high power drives, because at low switching frequency PWM, the switching power losses are very, very low in high power drives. And among the low switching frequency PWM, we go for selective harmonic elimination technique, or offline optimized PWM technique, or what we call as stored waveform PWM technique, where once the objective is known to us, objective may be reduction or minimization of weighted THD of voltage, or it may be minimization of pulsating torque, or it may be minimization of motor losses, or it may be minimization of total losses, that is the minimization of inverter losses and motor losses. Once the objective is known to us, then we can calculate the optimal values of switching angles alpha 1 and alpha 2, and maybe more than 2 switching angles alpha 1, alpha 2, alpha 3, for elimination of certain harmonics, selective harmonics, for suppression of harmonics, and for wide range of control of inverter output voltage as far as its fundamental component of voltage is concerned. Okay, so we have tried to understand the selective harmonic elimination technique or offline optimized PWM technique exhaustively using switching angle plane for 2 switching angles. First of all, we discussed one switching angle. We found that using one switching angle, we will be able to control the inverter output voltage, fundamental component, but harmonics we will not be able to control. Whereas using 2 switching angles per quarter cycle, or more than 2 switching angles per quarter cycle, we'll be able to control fundamental component of inverter output voltage and also suppress certain selective harmonics. Using the switching angle plane concept, we have tried to understand how we can control the inverter output voltage. We have developed the contours for controllable inverter output voltage, V1 contours, if you remember. We have also developed the contours for V5 equal to 0, V5 equal to 0 contours, that is 0 fifth harmonic voltage contours. We have also identified the 0 seventh harmonic voltage contours, that is V7 equal to 0 contours. Similarly, we can develop the contours for 0 11th harmonic voltage, 0 13th harmonic voltage, and so on. And once we know the contours for fundamental component of voltage, variable fundamental component of voltage, and we identify graphically the contours for 0 fifth harmonic component of voltage or 7th harmonic component of 0 7th harmonic component of voltage, we'll be able to find the areas, the regions, or the switching angle combinations, the locus of the point, which will give us PWM voltage waveform across the load in such a way that we will be able to control the inverter fundamental component of inverter output voltage and simultaneously suppressing or eliminating certain selective harmonics. Okay, and then we have seen how we can go for weighted minimizing weighted THD of voltage by choosing the locus of the point in such a way that V5 and V7 they are kept as low as possible. Okay, as far as locus of the PWM technique is concerned. We have also seen how we can choose the locus of PWM technique on the switching angle plane such that V5 by 5 minus V7 by 7, this difference is kept very close to 0 in order to suppress or in order to minimize the pulsating torque. And similarly, we can find the switching angle combinations in such a way that overall losses are reduced. And once we calculate these switching angles, alpha 1, alpha 2, and maybe alpha 1, alpha 2, alpha 3, alpha 4, using iterative numerical procedures like Newton-Raphson technique and other techniques, numerical techniques, we store those alpha 1 and alpha 2 combinations, switching angle combinations or switching angle pairs in the memory of computer in the form of a lookup table. And when we have to operate our load, maybe we have to control the speed of an induction motor. For the control of an induction motor, these switching angles are fetched from the lookup table, and we will be able to go for V by F control of the induction motor. By controlling frequency and voltage, we'll be able to control the speed of induction motor, and simultaneously we will be fulfilling the other objective, which may be minimization of weighted THD or minimization of pulsating torque, etc. Okay, so therefore all these selective harmonic elimination techniques which we have studied, they are offline techniques. The switching angles are calculated offline and they are stored in the form of a lookup table, and then they are fetched while controlling the load. Okay. The other type of low switching frequency PWM technique that we have discussed today is phase modulation. The advantage of phase modulation is that we can have a wide range of control of fundamental component of inverter output voltage from 0 to maximum, that is 0 to 4 pi VDC, but will not be able to suppress any harmonic component in the voltage. The voltage will be very rich in harmonics, so that's why this method is generally not used. So that completes our module number 2, which was focused upon low switching frequency PWM techniques. So I announced the end of module number 2, and now we are going to start module number 3. Module 3 of the syllabus, of the course contents. In module 3, we will be mostly discussing high switching frequency PWM. For low power applications and maybe for medium power applications like low power drives and medium power drives, we can go for high switching frequency. The switching frequency may be of the order of thousands of hertz. For example, we may have a switching frequency as high as 5 kilohertz, 7 kilohertz, 10 kilohertz, 15 kilohertz, 20 kilohertz. Okay, and or we may have a switching frequency greater than 20 kilohertz. Maybe, say for example, we may have switching frequency of 40 kilohertz up to 100 kilohertz. If our switching frequency is from 1 kilohertz to 20 kilohertz, in the inverter we generally use IGBTs as switches. And if our switching frequency is above 20 kilohertz up to 100 kilohertz, we use power MOSFETs. The switching frequency above 20 kilohertz, that's called ultrasonic PWM, ultrasonic switching frequency or ultrasonic PWM, because from 0 to 20 kilohertz the switching frequency, the inverter will make certain noise and that noise is audible to us. For switching frequencies above 20 kilohertz, it's outside the range of, outside the audible range of human ear. That's why it's called ultrasonic PWM or ultrasonic switching frequency. So for low power drivers and for medium power drivers, we can go for high switching frequency. For example, if fundamental component of voltages has a frequency of 50 hertz, and switching frequency of your PWM waveform is 5 kilohertz. That means 5000 hertz. The ratio between the two, the switching frequency to fundamental frequency ratio will be 5000 by 50. That is 100. So this is called carrier ratio. This is also called carrier ratio. This carrier ratio is represented by MF. It will be 100 for 5 kilohertz. If your switching frequency is 20 kilohertz, for example, for switching frequency of 20 kilohertz, what will be carrier ratio? Carrier ratio will be 20 kilohertz, that's 20,000 hertz by 50 hertz, fundamental frequency, that is 400. Carrier ratio will be 400. So we can have carrier ratio as it may be tens, of the order of tens or hundreds, like 100, 200, 300, 400 and so on. So we can go for high switching frequency PWM. Now in this high switching frequency PWM, in this module, module 3, we will be mostly discussing sine triangle PWM. We'll be discussing mostly sine triangle PWM. So we will have a fundamental sinusoidal reference voltage. We'll be comparing that with high frequency triangular carrier wave, and we will be generating the control pulses for various devices of the inverter in such a way that inverter at its output terminals produces a PWM voltage waveform, which when applied to a load produces nearly sinusoidal currents. Okay, if you take single phase voltage source inverters, let us start with high switching frequency of single phase voltage source inverters. For single phase voltage source inverters, various high switching frequency PWM techniques are: number 1, bipolar PWM technique; Second is unipolar PWM technique. Third method is bus clamping PWM technique. And fourth technique is even harmonic injection PWM technique. Even harmonic injection PWM technique. So we'll be discussing these techniques one by one. We'll start with bipolar PWM technique, and then we'll discuss unipolar PWM technique, then maybe a little bit of bus clamping PWM technique, and even harmonic injection PWM technique in single phase voltage source inverters. Let us today start with bipolar PWM technique. I will just give you an introduction of bipolar PWM technique. The first PWM technique, that is bipolar PWM technique. Let me draw the power circuit diagram of single phase PWM voltage source inverter again. These are the switches. This is TA plus, this is TA minus, this is TB plus, and this is TB minus. This is VDC by 2. DC bus capacitor voltage is VDC by 2, VDC by 2. This is O, and this is our total DC bus voltage, VDC. And we are connecting load between terminals A and B in inverter output terminals. This is the load. This is load voltage V0, and load current may be either in this direction or in this direction. Okay, fine. Now in bipolar PWM technique, what we do is that we have a high frequency reference sine wave. Sorry, it's not high frequency, it's a low frequency. We have a low frequency or fundamental frequency. Fundamental frequency means low frequency reference sine wave. This fundamental frequency or low frequency reference sine wave is compared in a comparator with a high frequency triangular carrier wave. So I have written here fundamental frequency or low frequency. I will write or low frequency. Fundamental frequency or low frequency reference sine wave is compared in a comparator, which may be an operational amplifier, op amp, in a comparator with a high frequency triangular wave, which is also called carrier wave. High frequency triangular carrier wave of fixed amplitude. So we have two signals. We have a low frequency or fundamental frequency reference sine wave whose amplitude is variable, controllable. And we have a high frequency triangular carrier wave whose amplitude is fixed. These two signals are compared in a comparator, and the output of the comparator produces control pulses or gating pulses for the IGBTs of the inverter, and it results in the switching of the inverter in such a way that a switched PWM voltage waveform is produced across the load at the output of the inverter. So it is something like this. See, See how comparison is done. You have to understand this. We have high frequency triangular carrier wave. So for example, let me draw triangular carrier wave. I may have to erase this power circuit diagram. I will draw it separately. See, this is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1, 2, 3, 4, 5. So let us consider 5 carrier wave cycles in from 0 to pi in positive half cycle of inverter output voltage, and then 5, 1, 2, 3, 4, 5 cycles, that is from pi to 2 pi for triangular carrier wave, 5 cycles from 0 to pi and 5 cycles from pi to 2 pi. Actually, you may have hundreds of such carrier waves. For example, if your inverter is switching at 20 kilohertz, that means the IGBT is switching 20,000 times per second. So in that case, the triangular carrier wave may have thousands of cycles per cycle. But for me, it is not possible to show thousands of carrier wave cycles per wave from 0 to pi, because the waveform will be too crowded. We will not be able to see the waveform like this. So for better understanding, I will take only a few cycles, say 5 cycles of carrier wave in positive half cycle, 0 to pi, and from pi to 2 pi, another 5 cycles. Okay, I will stop here for better understanding. But in actual practice, you will have large number of these triangular carrier wave. Now this triangular carrier wave, this is high frequency triangular carrier wave. It has an amplitude of VTRI. TRI means triangular wave. It has a fixed amplitude of VTRI. Okay, it may be 5 volts, it may be 10 volts. Now this high frequency fixed amplitude triangular carrier wave is compared with a controllable reference sine wave. So this is my reference sine wave, for example. This is the reference sine wave, and this reference sine wave has a variable amplitude V control. It's V control voltage, or iska amplitude and its amplitude is V control. Its peak value is this, but it is variable. You can vary it from 0 to maximum value. For example, if your triangular carrier wave has a peak of 12 volts, your control voltage reference sine wave may have a peak of 0 to 12 volts, 0 up to 12 volts. Similarly, 0 up to minus 12 volts. And then these two waveforms are compared in a comparator. And logic, what is the control logic? The control logic is very simple. Whenever triangular carrier wave whenever reference sine wave V control is greater in amplitude than triangular carrier wave, okay, upper switch is turned on. Let me draw the inverter. For that purpose, I may have to draw the inverter power circuit diagram. I will draw it here. I have no other option. I don't have space here, or let me draw it here. A compressed inverter diagram I will draw because of paucity of the space. I don't have much space available to me. This is my single phase PWM voltage source inverter. This is switch TA plus, this is TA minus, this is TB plus, this is TB minus. These are load terminals A and B, and the load is connected between A and B with load voltage V0, and load current may be in either direction as I0. This is VDC by 2, and this is also VDC by 2. Total voltage is VDC. Okay, the logic says whenever V control is greater in amplitude than VTRI, that is V control is greater in amplitude than VTRI, that is a reference sine wave has a higher amplitude than triangular carrier wave, then upper switch is turned on. What is upper switch? Let us take phase leg A, this leg. TA plus is on, and at that time TB minus, जो bottom switch है इसका TB minus, it is off at that time. And whenever V control is less in amplitude than VTRI, the bottom switch is on and top switch is off. So TB minus, which is the bottom switch of this leg, is on and top switch is off. So with this control logic, we can now see what happens. So now let us try to draw the inverter output voltage. Omega T. So we will draw the inverter output voltage VAB, which is equal to V0. So from this instant to this instant, you can see triangular reference sine wave is higher in amplitude than triangular carrier wave. Okay, and therefore in this leg upper switch will be on. और दूसरी leg में उल्टा logic है. For this leg when triangular carrier wave is for this leg the bottom switch has to be on. Okay, for this leg when triangular carrier wave is when reference sine wave is higher in amplitude than triangular wave, the bottom switch is on. So therefore in this leg upper switch TA1 is on, TA plus is on, and in this leg lower switch TA minus is on. So this is on, this is on. So A gets connected to positive DC bus, B gets connected to negative DC bus. What is total load voltage VAB? It is plus VDC. So this is my load voltage. It is plus VDC. And then from this point to this point, triangular carrier wave is higher in amplitude than reference sine wave. So logic is now just reverse. When triangular carrier wave is higher in amplitude than reference sine wave, then bottom switch in first leg is on and top switch in second leg is on. So this switch is on TB minus and TB plus. So since TB minus is on, A is connected to negative DC bus, and since TB plus is on, B is connected to positive DC bus. So what is VAB load voltage? It's minus VDC. So my load voltage is minus VDC. From this to this point, minus VDC. So therefore you can continue like that. Let us draw first of all these projections. Down. We'll draw all these projections, points of intersections. Very carefully we have to draw these points of intersections. That's it. So I got, so from this point to this point, reference sine wave is higher in amplitude than triangular carrier wave. My inverter output voltage is plus VDC. From this point to this point, triangular carrier wave is higher in amplitude than reference sine wave. My inverter output voltage is minus VDC. Then again, from this to this interval, reference sine wave is higher in amplitude than triangular carrier wave, and my inverter output voltage is again plus VDC because these two switches are on. And for this small interval, triangular carrier wave is higher in amplitude than reference sine wave, so opposite switches are on. My inverter output voltage is minus VDC. So you can continue like this. So this is inverter output voltage. So this is pi, and this point is 2 pi here. Now you can see this inverter output voltage is a pulse width modulated voltage, because if I move this reference sine wave up, the widths of these pulses will increase, and if I move this reference sine wave down, the widths of these pulses will decrease. So the motor, or if the load is a motor or any other type of load, how many voltage pulses it is getting across it? 1, 2, 3, 4, 5. 5 pulses in positive half cycle and 5 pulses in negative half cycle. So that means our IGBT switches are turning on and off 5 times in the positive half cycle and 5 times in the negative half cycle. So therefore the frequency of triangular carrier wave will determine the frequency of operation of these IGBTs. In other words, it will determine the switching frequency. So I will write here frequency of triangular carrier wave will determine the switching frequency. Switching frequency, Fs. If triangular carrier wave has a frequency of 5 kHz, my switching frequency of inverter will also be 5 kHz. If triangular carrier wave has a frequency of 20 kHz, the switching frequency will also be 20 kHz. And what about the frequency of fundamental component, frequency of the reference sine wave? The reference sine wave frequency will determine the frequency of inverter output voltage, because inverter output voltage is in the form of voltage pulses, PWM voltage pulses like this, positive half cycle and negative half cycle. Now you can see in the positive half cycle, the inverter output voltage starts rising from 0. It increases in every carrier cycle sinusoidally, and then it decreases, reaches pi, and in negative half cycle also it increases sinusoidally and then decreases. So this is fundamental component of inverter output voltage, V01, fundamental component. So therefore inverter produces a fundamental component whose frequency is same as the frequency of reference sine wave. So this is the frequency of reference sine wave. For example, if you want 50 Hertz voltage across the load, so your reference sine wave should be at 50 Hertz. So in that case, inverter output voltage will also have a frequency of 50 Hertz. If you want the frequency of voltage across the load as 20 Hertz, so therefore your reference sine wave can be at 20 Hertz. So inverter output voltage frequency will be same as reference sine wave frequency, that will also be 20 Hertz. So therefore frequency of reference sine wave, what does it determine? It determines the frequency, fundamental frequency of voltage across the load. It determines the fundamental frequency of voltage across the load. So I will repeat, the frequency of triangular carrier wave will determine the switching frequency of the inverter, and the frequency of reference sine wave, we determine the frequency of fundamental component of the voltage. Why I am saying frequency of fundamental component? Because this voltage, which is applied across the load, which is the PWM voltage, it will have fundamental component and harmonic components also. So what is important to us is fundamental component. So the frequency of reference sine wave will determine the frequency of fundamental component of the voltage. That's very important. So here we define modulation index. For example, we define something like this: amplitude modulation index, amplitude modulation index. It is denoted by MA. It is peak of the control voltage, reference sine wave, divided by peak of the triangular carrier wave. Okay, it's V control peak by VTRI. And similarly, frequency modulation index, frequency modulation index, which is also called carrier ratio or carrier ratio, MF. It is defined as a ratio of switching frequency of triangular carrier wave to frequency of reference sine wave. It is a ratio of switching frequency to fundamental frequency of inverter output voltage, Fs by F1. Okay. So these are very two important terms, frequency. For example, let fundamental frequency be 50 Hertz. That means inverter output voltage has a fundamental frequency of 50 Hertz. And let us assume the switching frequency is 5 kilohertz. So therefore, what will be the carrier ratio? Carrier ratio will be switching frequency divided by fundamental frequency, that is 5 kilohertz by 50 Hertz. That is 5000 Hertz by 50 Hertz. So switch carrier ratio will be 100. It will be 100 and so on. Okay. So why this is called bipolar PWM? Because you have seen the voltages are the inverter output voltage or load voltage. It jumps from minus VDC by 2 to minus VDC to plus VDC. Then plus VDC to minus VDC, minus VDC to plus VDC, plus VDC to minus VDC, and so on. Okay, if you draw it again, something like this. Seven, 8, 9, 10. 1, 2, 3, 4, 5. This is pi. And then 1, 2, 3, 4, 5. This is 2 pi. This is triangular carrier wave VTRI. So it has an amplitude of VTRI. And this is my reference sine wave. I'm drawing it again for your reference, for your understanding. This is reference sine wave, whose magnitude is variable V control, and it has a peak value of V control like this. So peak value V control. Okay, the inverter output voltage I will again develop. I will again draw for your reference. यहाँ से यहाँ तक. Let me draw these projections. I will draw inverter output voltage V0, which is equal to VAB. I am drawing these projections again for your reference. Okay. Reference sine wave is higher in amplitude than triangular carrier wave, so inverter output voltage is plus VDC. And then during this interval, triangular carrier wave is higher in amplitude than reference sine wave, so inverter output voltage is minus VDC. Minus VDC, I'm writing here, and then we can continue like this, plus VDC and minus VDC. And again plus VDC and minus VDC. Like this, plus VDC, minus VDC, plus VDC, minus VDC, plus, this is pi, this is 2 pi. The inverter output voltage, it will have a fundamental component like this. So this is V01, and of course this is V0. Now here is a question, why sinusoidal reference wave? Why sinusoidal reference wave? I have chosen the reference wave as to be sinusoidal. Why not square? I mean, my reference wave could have been square wave like this, square wave like this. This is also an AC wave. The answer to this question is why we have chosen reference sine wave, because if you see each carrier cycle, for example, if I see this carrier cycle, in this carrier cycle, the inverter output voltage is like this. It has a plus VDC and it has minus VDC, and it has certain average value. Maybe its average value is 0 because plus VDC is almost equal to minus VDC average value, and then it increases. In the next cycle, my positive voltage VDC is larger. I mean, it's for more time than the negative voltage. Plus VDC is for more time and minus VDC is for less time. If the time for which output voltage is plus VDC, we can call this time as T on, and the time interval for which voltage across load is minus VDC, we can call this T off. Now here T on is more than T off. That is, plus VDC voltage is applied across the load for more time and minus VDC voltage is applied across the load for less time. So therefore, what is average value? Average value increases because this positive area increases. If you find average, it increases. Move to the next carrier cycle. In the next carrier cycle, inverter produces this type of voltage. Now positive voltage on time again further increases and off time further decreases. So inverter output voltage, average value further increases and then it starts decreasing. So that means as you move with the reference wave from 0 to peak value, you can see the instantaneous average voltage in each carrier cycle increases. It is very small in the first carrier cycle. In the second carrier cycle, it increases. In the third carrier cycle, near the peak, it is the maximum. Then towards, when you go away from the peak of the reference sine wave, it decreases. Same happens with the negative half cycle. That means instantaneous average instantaneous pole voltage or instantaneous load voltage averaged over a carrier cycle over various carrier cycles increases sinusoidally. You take first carrier cycle. ये पहला cycle है. इसमें inverter output voltage है plus VDC minus VDC. On time is slightly greater than off time, so inverter average output voltage is very small, say somewhat like this. Go for next carrier cycle. ये आपका next carrier cycle है. ऐसे यहाँ से यहाँ तक. इस carrier cycle में inverter output voltage average instantaneous average voltage across the load increases क्योंकि ये the voltage across the inverter on time positive voltage plus VDC is for more time and minus VDC is for less time. जब आप इसका एवरेज निकालेंगे ये हायर होगा एंड यू विल फाइंड दैट इन्वर्टर आउटपुट जब आप इसको ड्रॉ करेंगे ये इस तरह साइनोसाइडली इंक्रीज होगा. Towards the peak of sine wave, the on time is highest than off time. So inverter output voltage एवरेज वैल्यू इस वोल्टेज का ये ऑन पीरियड है और ये ऑफ पीरियड. इसका जब आप एवरेज वैल्यू निकालते हैं, दिस इज ऑन पीरियड, दिस इज ऑफ, इसका एवरेज वैल्यू फर्दर इंक्रीज होता है और ये साइनोसाइडली इंक्रीज होता है. और जब आप व्हेन यू गो टुवर्ड्स द जीरो क्रॉसिंग, you can see the on time decreases, on time increases, on time decreases, off time increases. So average value, instantaneous average value over each carrier cycle decreases, and it decreases sinusoidally and it repeats in the negative half cycle. Okay, so you can understand it like this. अगर आपके पास बहुत सारे carrier cycles हैं, large number of carrier, और आपकी ये sinusoidal waveform, आप एक carrier cycle, just take one carrier cycle, so it will look like this. एक carrier cycle में, since number of carrier cycles is very large, it may be thousands for one half cycle of reference sine wave, so over one carrier cycle the reference sine wave will look sinusoidal. So let us take a couple of carrier cycles. ये मैं carrier cycles ले रहा हूँ, एक दो carrier cycles, and this is my reference sine wave. This is V TRI and this is V control. V control is actually sinusoidal, but over one carrier cycle it will be almost constant because large number of carrier cycles are there, and over this TS, the time period of carrier wave is much greater than the time period of reference sine wave. In other words, reference sine wave ka time period is much smaller than the time period of carrier wave. So over one carrier cycle the reference sine wave will look like constant. Okay, now you can see from this period to this period carrier wave is higher in amplitude, है ना, आपकी carrier wave higher in amplitude है reference sine wave से. So inverter output voltage will be minus VDC, minus VDC. और यहाँ से यहाँ तक reference sine wave is higher in amplitude than carrier wave, so output voltage will be positive, and then again it will be negative. So now you can see if this is off period, this is on period. On period is slightly greater than off period. So inverter की average voltage अगर आप निकालेंगे, this is the average voltage V01, उसकी average value. Now this may be somewhere here near this. If I go to the peak के पास क्या होगा, देखिए, what will be near the peak? Peak के पास carrier reference sine wave is high. See, you can see here reference sine wave is much smaller. Here near the peak reference sine wave increase होती है. Let us suppose this is reference sine wave. Now see what will be inverter output voltage. It will be minus VDC by 2 or minus VDC for this period, and it will be plus VDC for longer period, plus VDC. Then minus VDC for a small. इसका average value जब आप निकालेंगे वो higher होगा. This will be V01 higher. This has a small average value, this has a higher average value, and it increases in a sinusoidal manner. So when you move across from one carrier cycle to another carrier cycle, the instantaneous average voltage across the load increases, and it increases sinusoidally. It increases from 0 to peak, then decreases, then similarly the negative half cycle increases from 0 to peak and decreases. So it increases sinusoidally. So mathematically I can write like this. आपकी inverter output, I will write here average voltage. अगर मैं पोल वोल्टेज, although यहाँ मैं पोल वोल्टेज नहीं ले रहा हूँ, मैं आउटपुट वोल्टेज ले रहा हूँ. If I take average pole voltage, say VAO, that is given by 1 by TS integration 0 to TS VAO dt. This is the formula. आप TS means it's the carrier cycle. ये है आपका एक carrier cycle, इसका time period TS है. इसमें आप average pole voltage निकालिए. पहले carrier cycle में, फिर दूसरे carrier cycle में, तीसरे, चौथे, सारे carrier cycles में. एक carrier cycle में, this is the average pole voltage. So this average pole voltage is equal to, see, your pole voltage is either plus VDC by 2 or it is minus VDC by 2, right? So during the on period, it is plus VDC by 2. See, your pole voltage is plus VDC by 2 for T on period, and it is minus VDC by 2 for T off period. So I can write it is equal to VDC by 2 into T on during on period. This may be on period. During on period, it is plus VDC by 2. And during off period, it is minus VDC by 2. So minus VDC by 2 during off period, divided by total switching period. What is total switching period? It is on period plus off period, divided by T on plus T off. It's just like a DC to DC converter. In a DC to DC converter, how do you find converter average output voltage? You find it like this. You substitute during on time, this is the voltage. Off time, during this is the voltage, divided by total on plus off period, which is TS. So inverter output voltage. What is the duty ratio of a switch? In case of DC to DC converter, you know that duty ratio is defined by T on divided by T on plus T off. तो यहाँ पे अगर आप देखेंगे VAO is VDC by 2 into T on divided by T on plus T off, that is D, duty ratio of the switch, minus VDC by 2, T off divided by T on plus T off is 1 minus D. T on divided by T on plus T off is D, duty ratio, and T off divided by T on plus T off is 1 minus D, right? So therefore, I can find average pole voltage equal to VDC by 2. अगर मैं common ले लूँ, inside I get D minus 1 plus D. So therefore, inverter output voltage, average value of instantaneous average value of inverter output voltage is VDC by 2 to 2D minus 1. So therefore, instantaneous average output voltage, ये तो average instantaneous average pole voltage है. What is instantaneous average output voltage? Let us call that VA. That is equal to, see, output voltage switches from plus VDC to minus VDC. So I will not write VDC by 2. VDC by 2 I write for pole voltage. For actual inverter output voltage, I write VAB equal to, output voltage is VAB. इसका average value है VDC into 2D minus 1. So this is very important. So therefore, average pole voltage over one carrier cycle is VDC. Average load voltage over one carrier cycle is VDC times 2D minus 1. So as far as duty ratio is concerned, you see duty ratio here is low. As you move towards the peak of the reference sine wave, duty ratio increases because on time increases, off time decreases. यहाँ देखिए, यहाँ on time कम है, off time, on time और off time almost same है. Then on time increases sinusoidally, off time decreases. Then on time increases further, off time decreases. और फिर ऐसे. So as far as this duty ratio is concerned, it varies in a sinusoidal fashion. Sinusoidal fashion. Since it varies in a sinusoidal fashion, that gives the inverter output voltage, which is equal to VDC times 2D minus 1. Since it varies in a sinusoidal fashion, आपकी inverter output voltage, उसका fundamental component अगर आप निकालेंगे, that also, I mean उसका average value अगर आप निकालेंगे inverter output voltage, average value from one carrier cycle to or, that also increases sinusoidally. पहले carrier cycle में inverter output voltage, for example, छोटा value होगा. Go to next carrier cycle. In next carrier cycle, D increases, but it increases simultaneously. I mean sinusoidally. So inverter output voltage का average value बढ़ेगा, लेकिन ये sinusoidally बढ़ेगा. Go to next carrier cycle, near the peak. Inverter output voltage, no, on period is highest, on period is low. Inverter output voltage इसका average value सबसे highest होगा, so it will be near the peak. उसके बाद आप नीचे जाइए, inverter output, now you can see on period is decreasing, off period is increasing. So that means duty ratio is now falling, and it is falling sinusoidally. So fundamental component of inverter output voltage, उसका average value ऐसे sinusoidally decrease होगा positive half cycle में और negative half cycle में. So this is inverter output voltage VAB, उसका fundamental component. And what is the aim? हमारा जब whenever we use PWM technique, the aim is that inverter output voltage should be sinusoidal. It should be controllable and sinusoidal. Why sinusoidal? Because we want to suppress the harmonics. And that is achieved only when you choose reference sine wave as sinusoidal. You can see very clearly when reference sine wave is chosen as sinusoidal, the average inverter output voltage from one cycle to another cycle over the entire cycle 0 to 2 pi, the average inverter output voltage over various cycles, it varies sinusoidally, you can see. So therefore, अगर आप पोल वोल्टेज देखेंगे, your pole voltage VAO varies sinusoidally. एवरेज वैल्यू पोल वोल्टेज का साइनोसाइडली वेरी होगा. या आपकी VAO 1 फंडामेंटल कंपोनेंट, या एवरेज वैल्यू इट वेरीज साइनोसाइडली. और VBO भी साइनोसाइडली वेरी होगा, बट VBO विल बी 180 डिग्रीज आउट ऑफ फेज विद VAO. और आपकी टोटल वोल्टेज जो है VAB, उसका एवरेज वैल्यू फ्रॉम वन साइकिल टू अनदर साइकिल, इट इज इक्वल टू VAO माइनस VBO. इन दो का डिफरेंस आप निकालिए, तो यह आपकी VAB है. एवरेज इन्वर्टर आउटपुट वोल्टेज फ्रॉम साइकिल, वन कैरियर साइकिल टू अनदर कैरियर साइकिल, इसका एवरेज वैल्यू साइनोसाइडली वेरी होता है. So since inverter output voltage average, instantaneous value of inverter output voltage averaged from one carrier cycle to another carrier cycle over the entire cycle 0 to 2 pi, since it varies sinusoidally, that is why we choose reference wave as sinusoidal. अगर हम reference wave on the other hand ये choose करते, उसको triangular carrier wave के साथ ये करते, तो हमारी inverter output voltage का average value जो है, that would also have been square wave like this. तो उसमें high level of harmonic content होता है. But when we have chosen reference sine wave and compared it with high frequency triangular carrier wave, the instantaneous value of inverter output voltage averaged from cycle to cycle, it varies sinusoidally, so it will have low harmonic content. So this is the answer to the question why reference sine wave is chosen to be sinusoidal. आपको reference sine wave reference signal वही choose करनी चाहिए जो आपका objective है. Our objective is that load should receive sinusoidal voltage at a very low harmonic content. So that is why we choose reference wave as sinusoidal. So this is answer to this question. I will stop here. More on it in next class. Please go through this lecture and give me your feedback. All the best. Thank you.